Symmetric differences, Python's secret weapon, is isolate unique data across multiple sets instantly. Observe sets A and B. Our goal, extract values that are truly unique. Let's dive in. Value A is exclusive. It is completely absent from set B, but look closely at B. It is not unique. B appears in both sets. That makes it a shared item, not a unique one. How about the letter C? Let's verify. Spot on. C is nowhere to be found in set A. In code, we invoke symmetric difference on our first set. That's set A. Then we pass in set B. This method evaluates exactly two sets at once. Execute, and boom, A and C are our standout items. Perfect. Between sets A and B, A and C appear exactly once. Under the hood, Python tracks odd and even counts. It's pure set theory, but let's keep it practical. Here's the easiest way to master it. Time to level up. I'm adding a new set C. Notice set C also contains B. Now we chain our methods. We start with set A, call the method, and pass in set B as our first parameter. Then we chain another call for set C. This acts on the result of the first operation. Watch this. Python evaluates the first step completely before starting the second. This sequence is your key to mastery. But wait, there's a sleek shorthand. Ditch the long name for this clean syntax. It yields the exact same result. Simply use the caret or the hat symbol. It's the literal symbol for symmetric difference. The ultimate coding shortcut. Let's run the chain and see the output. Surprise! Something strange happened. A and C returned, but B is back. How? B is in set C, and in B, and in A. What's the logic? Here's the secret. Python drops even counts. It keeps the odd ones. A occurs once, so it's odd. Initially, B occurs twice. That's even. C occurs once, also odd, so B is dropped because 2 is even. But now, with 3 sets, B appears 3 times total. Once in each set, A, B, and C. Python processes this step by step. First, A versus B. It sees B twice, marks it even, and strikes it out. Gone. We're left with just A and C. We chain the next step, bringing set C into the mix. Suddenly, B is reintroduced. Remember, our running total only had A and C. In this new step, B appears exactly once. Since 1 is odd, it stays. That's exactly why B makes a comeback, and that is the pure magic of symmetric differences. Python lacks a native way to find unique values across multiple sets. Managing 3 different sets, there is no single magic function here. Instead, we will combine some high-performance tools, specifically the elegance of set comprehension. Let's dive in. In our demo, Team A uses Python and SQL. Meanwhile, Team B relies on SQL and AWS. Team C uses AWS, Docker, and SQL. The challenge: identify the skills that are truly unique across all teams. Scanning the list, Python stands out. SQL is everywhere, so it is definitely not unique. AWS is shared, but Docker is a loner. Python and Docker are our targets. These are the rare gems we want. First, we merge them using the pipe operator, creating a union. We are uniting every single item. Since we are merging sets, the result is naturally a master set. And sets instantly drop all duplicates. We are left with Python, SQL, AWS, and Docker. These are our base values. Running the code, boom! We see our 4 distinct technologies ready. Now for the real breakthrough, set comprehension. We need to count which of these master skills appears exactly 1 time across all 3 teams. We'll iterate through our master set of values. It acts as our master checklist. This builds our list of occurrences. As we check each item, we apply a strict filter. We only keep it if a specific condition is met. We only store a skill if its appearance count is exactly 1. Everything else is discarded. We use the sum function to tally it up. Inside sum, we verify the item's presence. Let's trace SQL. We check, is SQL inside Team A, Team B, and Team C? This check returns a Boolean true or false each time. It loops through the teams, testing for SQL everywhere. A match evaluates to true. Now here's the Pythonic secret. In mathematical operations, true equals 1 and false equals 0. So each check yields either a 1 or a 0. Summing them up is pure genius. Tracing Python, we get a 1, then a 0, then another 0. The grand total equals exactly 1. Condition passed. But look at AWS. It is in Team B and Team C. That gives us 0 plus 1 plus 1. That sums up to 2. The condition fails, dropping it from our results. Running the script confirms Python and Docker are the victors. Bookmark this technique. You just learned how to use set comprehensions like a pro to solve complex data problems with total elegance. Harness the power of combining loops, logic, and filters inside one clean set of brackets. Mastering this will instantly elevate your code. Python's counterclass is a total game changer. You definitely need this tool in your coding toolkit. It lives in the collections module. Let's start by importing it. Here is a perfect example of how it works in practice. Imagine we have 3 different groups: Team A, Team B, and Team C. Each team uses specific tools within their environments. Team A works with Python and C. Our mission: find tools used by only one single team. We want to find items with a count of 1. This is a very common challenge in data. You often need to identify unique occurrences quickly. Take a look at Python. It only appears once here. But look at SQL. SQL is definitely not a unique case. It shows up 3 times. AWS appears twice, while Docker appears once. So how do we track this? First, we'll initialize a variable for our counter. Once that is set up, it gives us a clean, empty class to work with. Next, we will iterate through our 3 teams. Remember, these teams are stored as sets, individual sets. We've created a list to loop through them all. Team A, Team B, and Team C. Each one is a set. You can see the set type when I hover here. Now, we call the counter's update method. Our variable is now linked to that powerful class. This update method is where the real magic happens. It is incredibly efficient. We pass in the current team. The first pass handles Team A. The loop then moves automatically to Team B. And finally, Team C. Each one contains our objects. Let's run this so you can see the result. It generates a dictionary. The counter creates this map where SQL starts at 1. This is just the first pass. Since we have SQL and Python, Python also gets a count of 1. It's a standard dictionary. There's the key, and there's the value. On the second pass, look at SQL again. This is Team B's data. The count hits 2 because the counter updated dynamically. That team also used SQL, so it climbed from 1 to 2. AWS was just added, even though it wasn't there before. Now we have those values. The process continues for Team C. SQL is now 3 because of that third instance. AWS reaches 2. Python stays at 1, and Docker joins the list with a 1. Now for the finishing move, list comprehension. We simply loop through our final counts, checking every item. Since this is a dictionary, the items method gives us exactly what we need. We are going to extract the specific count and then store the name of that tool. If the count equals 1, we save it as unique and print the result. And there they are, Python and Docker. This is incredibly useful. Grab it from the collections module and use that update method. It's the fastest way to organize your data, using clean Python comprehensions for the output. What exactly is a Frozenset? In Python, a Frozenset is a collection you cannot modify. You've seen the syntax for a standard set, which starts with curly braces at the beginning and the end. But for Frozensets, you must use the class name Frozenset and then pass in an iterable object. In this example, we will pass it a simple list. Once created, a Frozenset cannot be changed. No matter what you try, it remains constant. This immutability is crucial because this is where the real technical advantages kick in. Think about managing session permissions. These include reading reports, exporting data, and dashboards. You don't want any part of your program to alter these. You want these permissions to stay fixed for the user. This makes your code secure, as no other function can. Accidentally modify user permissions. Running this, we see the login permissions. Export data, view dashboard, and read reports. Let's verify them here. We'll print a label to check if export data is allowed. That is our permission. Is export data within those session permissions? Since it is, Python returns true. Now, here is where Frozensets become incredibly handy. Look at this team registry. We want to check if a specific team exists within our records. If we have Ben and Alice added as a new group, we need to verify it. You might think the standard syntax works. We start with a set, and inside that, we nest another set. This fails because sets are unhashable since they change. You can't nest them. Instead, you can use a tuple or simply wrap the inner data in a Frozenset right here. Unlike a normal set, a Frozenset is fixed and hashable. This allows you to create unique combinations. Now, the code works, confirming the team with Ben and Alice exists, returning true. A normal set cannot do this. That's why Frozensets are essential. Notice the syntax. Use the class constructor and pass it the required list of team members. Another great use case is when user requests arrive in a different order. You can create a Frozenset for user 42 and save. If the user sends the same data but changes the order, placing action, save first and user 42 second. They are now reversed. This is where the Frozenset makes a huge difference. The order of these elements doesn't matter. It compares the incoming request with existing ones. If they match, it returns true, already processed. The sequence had no impact on the result. Again, we used a Frozenset to nest a set within a set. This is a unique feature of Frozensets, and that is why you need them. They are immutable. Remember this part. They are immutable, unordered collections of unique items. You can't change them, but you can nest them in sets. Standard sets of sets are not allowed, but using a Frozenset works perfectly. Python sets offer incredible built-in methods, and one of the best is disjoint. This method identifies if there is any overlap between your sets. If they are unique, it returns true. If it returns true, you know for certain that there are no overlapping elements. However, if it returns false, a common element exists. So it returns true specifically when two sets have no intersections. Now, let's see this in practice. It might sound technical, but the logic is very simple. Let's take a look. We have user permissions and a list of restricted actions. In a secure system, users should never access restricted actions. For instance, deleting users or shutting down the server is strictly forbidden. But if a user only has permission to view reports and edit profiles, there is no conflict. To verify this, we take our first variable, user permissions, and call the isDisjoint method. Then we pass in the permissions we want to check against. If there is no overlap, the system confirms it's safe and returns true. Running the code, you can see the result immediately. There is no conflict, so it returns true. But what happens if permissions actually overlap? Let's find out. In this case, we have a conflict. The user can view reports, but they also have delete users, which is a restricted action. What do you think? This method will return. It will return false. Running the script, we see that false is indeed the output. This warns us that the user account has excessive permissions, and we need to take action in our code. IsDisjoint checks for any intersection between elements. If it finds one, it returns false. Otherwise, with no intersection, it returns true and you're good to go. While I'm using Frozensets here, this works perfectly with normal sets too. IsDisjoint is a versatile tool for both set types. The key difference is that Frozensets are unchangeable. You cannot modify them once they are created. This is a vital security feature. You don't want any part of your code to accidentally alter restricted actions. Frozensets prevent these accidental changes entirely. With a standard set, you can still make modifications, but that leaves room for errors elsewhere. One essential method you must master when working with sets is isSubset. But how do you actually determine if one set is contained within another? In other words, is it part of it? There are several ways to do this. Do you know how they work? If not, don't worry. Let's break them down. Take a look at this Frozenset. A Frozenset is a collection that cannot be modified. It is completely immutable. So you have standard sets and you have Frozensets. Just remember, Frozensets never change. That is the crucial distinction. Here, our required permissions are set to read and write. However, this user has permissions to read, write, and delete. The big question is, are the user's current permissions a valid subset? Essentially, we want to verify if the required set is contained within the user's set. Let's look at the logic. Here, required is indeed a subset of what the user possesses. If it matches, the comparison returns true. Now, here's where beginners often get confused. The less than or equal to sign. This operator is another way to check if a set is a subset. When we run this code, it confirms the subset is valid, even though the user has more permissions. than the original required set demands. So this returns true. The second check also returns true because it is definitely a subset. The user has everything required. But watch what happens when we change the values. Notice that now both sets are identical. The required and user sets contain the exact same elements. Running this, the less than or equal to comparison still returns true. However, using only the less than symbol returns false. This is because the sets are equal. One is not smaller than the other. Technically, it's not a proper subset. Since it's not a proper subset, the less than symbol returns false. Yet, less than or equal to is true. They are perfectly equal. Both have read and write. The reason the first example worked was that the user had more than what was strictly required in the read and write set. The user also had delete that made it a subset. That is the core test. Is it a subset? Less than or equal to says yes. They are subsets, and in this case, they are exactly equal. Mastering dictionaries is a total game changer in Python. They power everything. You'll find them in APIs, backend systems, and secure configuration files. They handle automation, data processing, and complex scripts with ease. Let's dive into how they actually work. In Python, we define a dictionary using these curly braces. Inside, we store data as key-value pairs. A colon separates the key from its value, and we separate each item with a comma. Take a look at this first element. The key is hostname. Hostname is our unique identifier, and API 101 is the actual value. Next, we have status as the key, and online is its value. Then we have request as the key with a value 18420. Let's print this out. Running the code, you can see the host name displayed clearly. There is the colon, followed by the value, API 101, and there's the comma separator. That completes our first dictionary item. Then comes the second pair, and finally the third. Notice how those curly braces wrap the entire data structure? The beauty of this is that you can access data by name. Forget about using index numbers like you would with a standard list. Now you can simply call the item exactly what it is. From our server variable, we want to grab the host name. We just type it in. And boom, we get API 101. But stay sharp. There is a major rule you need to know. What do you think happens here? We have a project variable holding a dictionary. The project name is Atlas. But then we have another key called Nova. What's the result? This is the one gotcha that often trips up beginners. It's not what you might expect. Python will actually overwrite the first value with the new one. As we run this, notice how only one of them remains. The second value simply replaces the previous one. You must keep this in mind when coding. If you reuse a key, the last one defined is the survivor. The old value for that key is gone forever. Watch out for that as you start building. Stop accessing dictionary items like this. Do you know why? Stick around to find out. Here is our basic inventory dictionary. We have 42 keyboards in stock, and we have 419 mice. Simple enough, right? This is our current stock. But look what happens when we search. For a monitor, it doesn't exist. Running this code triggers a total failure. The dreaded key error. It says monitor was not found. How do we fix this? This is a disaster. Don't let this happen. Instead, we need to use a much smarter approach. Use the built-in get method for your dictionary. It still looks for the monitor, but with a twist. You provide a default value. Looking at how this function works, we provide the key we want to find. There it is, and here is our fail-safe fallback. It returns the value if found, or the default if not. Watch. We search for the monitor again and set the default to not in stock. Now, it prints not in stock instead of crashing. But if we search for an item that is there, we get the perfect result, 42 for the keyboard. Stop using direct access and risking a crash. Use the safe get method. This is the pro way to code. It prevents crashes and keeps your users happy. Always use the get method. Escape the error hellhole forever. Let's update some dictionary items, but keep a close eye on this crucial detail. It can be a huge time saver or a total headache, depending on your goal. Check out this sessions object, where we're tracking our users. We have Alex, who's active, and Mia, who is currently marked as idle. Our goal is to switch Mia's status to active. Sounds simple, right? It actually is. Let's run the code and see the result. Alex is active, and now Mia is successfully active too. But here's where things get interesting, and maybe a bit confusing. We're using the exact same logic here. We still have Alex and Mia, but now we have Allison. We want Allison to be active as well. However, Allison doesn't exist in our dictionary yet. She isn't an existing key, so what do you think happens next? Think fast. You've got 3 seconds before I reveal the answer. The answer is Python will add Allison to the dictionary, even if she wasn't there before. This syntax doesn't just update existing keys. It automatically creates them for you on the fly. Watch this. Alex is active, Mia is idle, and suddenly, we have Allison. She's been appended and marked as active. If that wasn't your intention, it's a major surprise, but that is exactly how it works. So how do we handle this better? You should probably use the .get method to check if Allison exists before trying to update her. If she isn't there, you can choose a different path. This specific behavior is a must-know for every Python developer. If a key exists, Python updates it instantly. But if it's missing just like Allison was, the code will actually create a brand new entry. A new key is born along with the value you supplied. Master this logic and you'll handle dictionaries like a pro.